People have liked the recording so far. So just to reiterate, since I'm just starting to record, we're looking at the symbols in a chemical reaction and their meaning. And so with the meaning, you can convert the set of symbols of a chemical reaction back into a sentence form. So the arrow means yields, the plus sign means with, and then we have various states: solid, liquid, gas, and then not a state, but a condition, aqueous, of being dissolved in water, our universal solvent. There are other symbols as well. So let's just show another set. These ones are perhaps older a little bit, but arrow up means gas evolves, usually from a liquid. We'll put that. Arrow down means precipitate. And I think we've talked about precipitate forms, usually from a liquid. There's a few others. Let's see, what else have we got? We have this one. We've seen this symbol before. This is the Greek symbol, capital delta. And so in a broader sense, it means change, but in a chemical reaction, it generally means heat added to the reaction. That's a pretty good set of symbols. There's one more that I would add. Since we did our quantum mechanics, H nu is sometimes put in to mean light, right? Light energy specifically, right? Frequency times Planck's constant gives us energy. And so some reactions either give off light energy or absorb light energy in order to happen. And so with that, we can write chemical equations. So let me write here. How about okay, so can I take this set of symbols and convert it back into a sentence? So that might be like a skill that you might encounter in the homework set. Can I change this? What would I do? So I'd start with this one. And so this forces us to go back to our naming. Anybody remember the name of that? So anyone want to? Oh, someone said iron 2. Well, not quite. So we have to go back to the naming. Okay, someone said iron 3. So remember, it's not the number of irons, but rather the charge of the iron. There's 2 iron 3 pluses. Let me write that above. 2 Fe 3 plus 3 O 2 minuses. Yeah. Okay. So iron 3 oxide, and I guess we could add the word reacts, and then I can put that plus sign, I guess. So they're on the left side, so I add reacts, plus sign with solid aluminum. I should have said iron 3 oxide solid. This is kind of an unusual reaction, actually, where a solid reacts with another solid. It's quite uncommon. With solid aluminum so go to the arrow, to yield solid iron. And, well, this one won't have a Roman numeral because aluminum is a fixed charge. So we'll just call it aluminum oxide, solid. right? And all of that is contained in the set of symbols. So it's a much faster, quicker way to do that. Now you may notice, does anyone notice there's a problem with the chemical reaction that I wrote? Can you see the problem? Let's look at the iron here and the iron over here. Do you guys see something strange?
It's not balanced.
It's not balanced. And so,
It's not balanced.
it's not balanced. Good. And so that's kind of leading me to the next idea, that chemical reactions observe conservation of mass. You guys remember conservation of mass? It's a simple statement. No, remember it? Matter cannot be created or destroyed, right? And so there's two corollaries to that statement. The first statement is the total mass of the reactants. If matter can't be created and it can't be destroyed, then the matter that we start with has to equal the matter that we end with. The total mass of reactants equals the total mass of the products, right? So if we, and let me balance, let's do a balanced chemical. So if I have 2 hydrogen react with 1 oxygen to make 2 water, over here I would have, let's see, that would be 2 times 2, 4.04 grams of hydrogen reacting with 32 grams of oxygen. And by golly, that would equal 36.04 grams of water, right? So this total here, 36.04 grams, has to equal this amount here, 36.04 grams. Okay, so and you guys can ask questions. If I don't hear anything, then I'm assuming I'm going at the right pace and you're okay. So you're okay to, you know, say something if you want. We have time, I believe. Okay, so that's just the first corollary. The second corollary involves balancing. Second corollary is I have to have the same number and kind of atom on both sides of the equation. And so that's where the balance, this is where the idea of balancing comes in. And so for balancing, I guess the key idea is, well, let's have a couple of key ideas. One key idea is I'm going to balance with coefficients. Is it okay if I do W/ for width? I think I did that in lecture long ago. Balance with coefficients, meaning do not change formulas. Right? So it might be tempting if I see hydrogen plus oxygen goes to H2O, it might be tempting to just kind of say, oh, you know, I'll put in a little 2 there, right? If I put in that 2, well, gosh, if that reaction happens at all, I'm describing something else. That's no longer water, that's hydrogen peroxide. So I wouldn't do that at all. Okay, so do not change formulas. Let's put another key idea is you use the lowest common multiple. And this is similar to when we did naming. All right, so let's go back to our problem. We had hydrogen plus oxygen goes to water. So I'm ignoring the states just so I can focus on the balancing, which is okay to do, I guess. Is that blue? Oh, cool, blue. All right. So we're gonna bump out in 10 minutes. I'd like somebody, since there's 20 of you, if you guys can let me know when I hit the 1 minute mark. Can you see the timer up there? It says 9:39, 9:38, going down. Okay. So just let me know when I hit 1 minute. We'll bump out and then bump back in, and that's fine too. Since I'm recording this, I think it's nice. It's easier to upload. It's actually hard to upload because it's a lot of data. But a 40-minute block is certainly a lot easier to upload than like an hour and a half or a 2-hour block. And then the student, it's easier for them to sort through that material. Okay, so use lowest common multiple. So so how would we balance this? If I look at this equation, if I look at the hydrogen, how many hydrogen are on the left? Anybody? How many on the right? So someone's typing in 2. There's two both on the right and the left. Okay, and someone's already got the answer. This one's an easy one, but let's go through it. If I look at the oxygen here, there's 2 here and there's 1 there. So the way it's written, there's an oxygen disappearing from the universe. Oh, am I at time? No, I have 8.5 minutes or so. Okay. So oxygen's disappearing from the universe. I can't change the formula. I can't go H2O2. So I'm going to put, let's go blue. Let's see if blue comes up. I'm going to put a big 2 right there. And I changed the number of oxygen. So now it's balanced. But now I've changed the number of hydrogens. How many hydrogens are here? No, when I said when I have only a minute left, I'm sorry. Is that okay? Okay. So someone's saying I have 4 hydrogens here. So let me know when the clock only has 1 minute till the meeting ends. That was the don't let me know in 1 minute from now, but in 1 minute till end, and then we'll start over. So there we are. So now we have 4 hydrogens there. We still only have 2 there. Can I fix that? What would I do? Someone says yes. I'm going to put 2 hydrogen molecules. And then now it looks like it's balanced, right? So that one's a straightforward one. Let's do a few others of these just for some practice. And let me give you, so again, these, you got to kind of follow these as your guiding. Keep balance of coefficients. Do not change formulas. Keep the lowest common multiple. And then usually the steps that I follow when I'm balancing is 1, I balance metals. Now, when you get more adroit at this, then you can, you might say, oh, I want to balance the nitrogen because that looks like a mess. But in general, this is a nice way to go if you're starting out. Balance metals. 2, balance non-metals, comma, except hydrogen, oxygen. Those are the hardest to balance. So hydrogen is the most abundant element in the universe. It's 99% of matter when we look out to the stars. Oxygen is the most abundant on our planet. It's over 50% of the mass of our planet. And so there's so many compounds with oxygen on our planet. So generally you balance the metals, then the non-metals, then you balance hydrogen, and then you balance oxygen. And sometimes if you go through the step, a lot of times oxygen and hydrogen may work themselves out by the time you get to the end. And that's kind of your basic idea. Let's do some others. We'll do a couple. How about calcium hydroxide? Oh, and let me add another idea is if they're if there is an unchanged polyatomic ion, you can count that as a thing. I'll just call it a thing. Is that all right? Or pretend like it's an atom, if you will. All right. So this one's not going to be that case. So here we have calcium hydroxide reacting with hydrochloric acid to make calcium chloride and water. Did I run out of room? I guess that's okay. All right. So let's balance this. So where's the metal? Is there metal? Oh. Yeah, so someone's asking about solubility rules, and I will get to that. Actually, in the lab, if we don't have time tonight, we will definitely talk about it during the lab time. And there's already videos uploaded in the lab of talking about solubility rules. But I will try to get to that, but we have to do this first. Okay, so okay, I hope that's okay to table that. Okay. All right, so let's look at this equation and let's say to ourselves, okay, self, what's the metal here? Are there metals here? Are there metals? Is anything a metal?
Calcium. Oh, you balance calcium first.
Balance calcium. Okay, so I'm going to look at calcium. How many calciums? And if you want to, sometimes people will do this. They'll say, okay, calcium, and they'll do like a balance sheet, products and reactants. Over here I have 1. Over here I have 1. Calcium's balanced. So what would I go to? Probably.
Then you would go to chloride?
And I'd go to chloride. All right, so I'd go to chloride. I look on the reactant side, and 1 and 2. Okay, so let's fix it. Let's change that. How will I fix it?
You put a 2 in front of HCl.
Perfect. I don't want to change the formula, so 2.
That gives
chloride's balanced. Okay.
So you would be missing 2 hydrogens on the right side, and then you would add a 2 for H2O, right?
Okay, so let's look at that. So yeah, I think someone's already solving it, and that's cool if you guys are with me. I'm going slower. How many hydrogens are in calcium hydroxide?
4, no 2.
2, and in HCl?
That makes it 4.
Yeah, so I have 4 HCl now that I balanced the chloride. And then how many do I have over here?
2.
I have 2. So let's fix the hydrogen then. How will I fix it?
You add a 2 in front of H2O.
I'll put a 2 in front of H2O. Now it's 4.
And that solves everything.
Yeah, and then the oxygen worked itself out. So I have 2 oxygens here, and then I have 2 over there. Voila. And that's kind of my plan. That's how they tend to roll. Let me do a harder one. Is that okay? So let's continue. Oops. Okay. So let's keep the same ideas. Okay. Let's have a polyatomic ion that stays unchanged. How about that? Let's do one of those.
You have less than a minute.
Oh, thank you. All right. So I'm going to end right now, and we're going to jump back in. And this is good because this is like a 30-minute chunk of material. So I'm going to stop the recording.